Okay, so we're mid chapter 16 because we covered the first 3 sections last 2 weeks ago before Thanksgiving. So let's review what we learned so far about waves. Remember, chapter 16 and 17 are all about waves. Okay, so we learned how to write the equation that describes the motion of a wave. So remember, y is sort of like the amplitude, or actually the vertical motion. So you have a wave like this, right? And it's wiggling up and down, let's say in this green, right? Okay. Let's say this is position, this is y as a function of position, right? The equation that describes it is just some sine wave, okay? But there's some complication inside that sine wave because here you have this factor called the wave number. K is not the spring constant, right? Times the position. So how far is basically a sine wave as a function of x. But it's also a sine wave as a function of t, where t is multiplied by this angular frequency / velocity. They actually mean the same thing because they're actually the same if you compare them to the simple harmonic motion. So if you plot this versus time, you will see the same function, right? We did this exercise the first time we play around with waves. Okay, you'll see the same function. Well, it looks exactly the same, but one is versus position, the other one is versus time, because we're trying to show this two-dimensional, right, motion of things, where it's moving in space and time at the same time. Okay, and with all these other properties about waves, right, there's the amplitude of oscillations, amplitudes of the wave. Okay, you can see how I'm mixing oscillations and wave because they're actually the same concepts, okay, applied to slightly different physical systems. There's the period of the wave, okay, and the period is related to the regular frequency by this factor of 1 over the period is actually the frequency. Just to tell you what the frequency is, right, is how many frequencies tells you how many cycles per second versus radians per second. Cycles per second is actually known as a hertz, okay, which is actually the angular frequency, which gives you number of radians per second, right, divided by 2 pi. Okay, this 2 pi is just kind of a conversion factor between the two. The new thing about waves is that you also have this thing called wavelength. The wavelength is basically how long does it take in space for the wave to repeat itself, right? Where the period is how far ahead in time will the wave repeat itself. Okay, so those are two different ways to, one quantifies how does it behave spatially in the x direction. The other one describes how does it behave in the time coordinate system, which is the amount of time it takes for it to repeat itself. And there's also this complicated differential equation that we don't really try not to avoid it as much as we can, but there's some interesting thing about it where, right, the left-hand side is derivative with respect to x. The right-hand side is derivative with respect to time. So you're taking derivatives with different variables. And the factor that relates the two is actually 1 over the speed of the wave square. When we actually use this to find the speed of a wave that is on a string under some tension, right? Some tension F sub t, which is the tension force, how much you're pulling on that string, okay? Divided by the mass density of that string. And we're gonna play around with that today, actually. And the important thing is not to memorize this formula, is to get the idea that, right, the speed of the wave is related to some square root, just because of this square situation here, right? Some elastic property, meaning how stretchy the spring is, right? And we'll also talk about how compressible fluids are, or we talk about speed of sound in the air and stuff like that. And then some inertial properties, meaning how heavy it is, right? This mu thing is the mass per length, right? How heavy that string is per length. And that's the idea of this elastic versus inertial properties. So as you deal with waves that are not just waves on a string, you should think about this versus trying to figure out this formula, right? Because, right, you're not, if you're talking about sound wave, you don't have a tension on the sound wave, right? You just have the compressibility of the air that's actually causing the sound to propagate forward. Okay. So now we're going to do one more additional analysis. Well, one more additional analysis is to examine how waves behave when we're trying to figure out how much energy is being transferred through a wave. Okay, right. So hopefully by the end of this lecture today, we're going to be able to see how energy travels through a pulse of wave, specifically waves on a string. Okay, and we're going to try to find some mathematical expression that allows us to figure out how much power is being sent by a wave once it travels from the left to the right. Not just simple things like this, like these are known as a string vibrator. It's just a way to make a wave. But also, if you pluck a guitar string, right, how much sound energy is being emitted by that guitar string, or like a tsunami wave hits the coast of California or something like that, how much energy is actually being transferred by those types of waves, okay? I'm going to try to figure out how we can quantify those. All right. So to quantify things, as usual, what we're going to do is we're going to zoom in and stare at a tiny, tiny piece of the system and try to figure out how that little tiny piece behaves, okay? We're going to do this little tiny piece on wave on a string. So this is the big wave, but we're going to stare at this little tiny little piece of it and just kind of figure out, okay, how is it moving up and down? How much energy is it carrying around as it moves up and down, okay? Since something is moving up and down, whenever something moves, it has what type of energy? Going back to chapter 8. What kind? Kinetic energy, exactly, right? So kinetic energy, let me use the better color. Kinetic energy is 1/2 mv squared, right? So that's always the formula for kinetic energy. Since we're dealing with this little segment, tiny mass here, this little segment is actually moving up and down, right, with some velocity, Vy, right? It's only moving up and down, right? It's not moving left and right, right? The string is not physically getting, moved forward, right? It's just wiggling up and down, up and down, up and down, right? So there's only motion in the Y direction. So the little tiny amount of mass, right, has this tiny amount of kinetic energy, okay? And we're just going to plug in, right, 1/2 the mass of that object. The mass happens to be just this delta M that we just defined. And then the speed of that object going up and down square, right? 1/2 mv squared, right? So you see how this is the mass, right? And this is the speed that is going down, up and down, right? Okay. And we're going to do is that, well, this little tiny piece of mass, we can relate that once again to the length mass density. Remember this mu here? Mu is, in English, we just can say, right, it's the mass density. Okay, so in English, what we'll say is that how much mass per length, right? That's what we should think about when we see this letter mu in this case, right? How much mass does it have per length, okay? Well, the amount of mass it has per length, right, times, the length of the object, right, gives us how much mass, right? If you take, something that has a mass density of 5 kilograms per meter, you have 1 meter of it, you have 5 kilograms. You have 2 meters of it, you have 10 kilograms, right? You have 3 meters, you get 15, and so on like that. Does that make sense? You multiply the density times the length, you get the total mass, right? In this case, the total mass we're interested in is just this little tiny segment of mass, okay? And you can see that these delta is going to turn into some calculus trick we're going to do in a second, right? Because typically we'll take the limit as this delta x goes to 0, okay? So rewriting this delta m here as mu times delta x, well, we just kind of plug in up here, right? You get this equation down here, right? Where it's 1/2 instead of delta M is mu times delta X, right? That's all I'm replacing. Okay, so a lot of little steps, but just to understand how this works, we're going to try to go through them, maybe not too quickly, hopefully. Okay, so what we're going to do, since we have a little delta X thing, we're going to take the limit as this delta X goes to 0, right? This is where the calculus stuff comes in, right? When you have a delta something, you take the limit, right? It turns that delta into a derivative, right? Or it's actually technically a differential, right? Instead of delta X, it's just dx. Okay, so now we've done this like so many times in this class, right? Okay, so the other thing to note is that while the velocity in the y direction, right, is actually a derivative. I don't like these partial stuff. Let's not dwell on them. So we can just write that as dy dx, right? Let's try to, I'm going to write it here. Okay, think of it as derivative dy dt, right? It's the time derivative is actually velocity. Okay, and we actually have an equation for that because, right, when you take a derivative of a sine function, it gives you a cosine function and it pops out. Since we're taking derivative with respect to time, it pops out a negative negative omega. Okay. So we actually have an equation for this. Okay. Now we plug that back in here, right? Plug this all the way up in here. Okay. There's a lot of factors to keep track of, but it's not super important that you know every one of these steps because this is also in the textbook. So we're going to get to the end hopefully pretty soon, and that's the equation you actually want to make sure to copy down. But just to see, we can go through these steps. Okay. Okay. Well, the negatives cancel each other out, right? You got power 2 here. You're basically squaring this. Okay. So the end equation here basically is 1/2 mu times some derivative of some differential of x, the amplitude square, omega square, and some cosine function square. Okay. That's only the amount of energy carried by this little tiny segment of mass, right? In order for us to figure out how much energy is carried by the entire wave, we have to add up all the little tiny segments, right? When we add up a bunch of tiny little segments together, right, that means doing a integration, okay? We'll show you the integration here, so you don't have to do it yourself, okay? So what we want to do is actually be able to integrate this function here, okay? Okay. When you do this integral, it's this cosine square, okay? Don't worry about that. We have to do this type of complicated integral, okay? The answer turns out to be, we can even skip the middle step here where we're evaluating the integral, okay? The answer turns out to be 1/4, okay, times the mass density times the amplitude square times the frequency, angular frequency square times the wavelength, okay? Don't write this equation down yet because there's yet another thing we have to account for, okay? The other thing we should account for is also that since the string is under tension, that tension is a spring, right? It's kind of like a spring, right? That spring is also storing energy, okay? When we compute the energy stored in a spring is 1/2 kx squared instead, right? As opposed to mv squared, okay? At k, so the spring constant can be converted, just by doing a little bit of algebra, is that it's just going to be omega squared times mu, this mass density, okay? We won't go through all the algebra steps, but the main point is that what happened is that the spring potential energy also gives you a factor of 1/4 mu times a squared omega squared times the wavelength, okay? They're actually exactly the same. Those of you who are going to go on to take either physical chemistry or thermodynamics from physics, this is actually known as the equal partition theorem. It's actually very interesting that the kinetic energy and potential energy gets equally partitioned in a complex system like this, okay? But since we're adding 2 1/4 of stuff, right, right? When you add them together, since these factors are exactly the same, right? Mu times a squared omega squared times lambda, right? You get a 1/2 instead, right? 1/4 of something plus 1/4 of something gives you a half, right? A quarter plus a quarter is $0.50, right? That's all we're doing, okay? So the actual equation we want to write down is to figure out, well, if we divide this by the period of the wave, which kind of tells us like how much energy per period it has, okay? We actually get the power output of the wave, okay? And that's what we're actually interested in, this orange box, okay? When we divide by the period, right? Period divided by, sorry, the wavelength divided by the period is actually the velocity of the wave, okay? Remember that velocity is equal to lambda times f, and then one, since f is 1 over the period, wavelength over the period is actually the velocity of the wave, okay? And this is the actual equation that we're going to be using a lot in this section, okay? The power of the wave, okay, has this factor of 1/2, okay, and that comes from adding 2 quarters together, okay? The density, the mass density of that particular string, okay? The amplitude square, and then the frequency square, well, the angular frequency square, it's the omega, not the f, right? Times the speed of the wave, okay? It's a long, complicated equation, but if we can figure out all the variables in there, we can calculate what the power, how much power a wave actually gives off, okay? The take-home message is that this power is actually proportional to the amplitude square, okay? This is gonna come back to us when we talk about stuff in chapter 17, when we talk about sound waves also. So that's sort of the take-home message, okay? To make sure that you know that, okay, the amount of power emitted by the wave that is basically, if you have a wave that has an amplitude of 1 meter, right? And then you compare it to a wave that has an amplitude of 2 meters, it's 4 times more powerful, not 2 times, okay? Okay, because you're squaring the amplitude, okay? This is actually the same in the case of the simple harmonic motion from chapter 15. I know it's from a long time ago. The amount of energy stored in a simple harmonic oscillator is 1/2 the spring constant of that harmonic oscillator times the amplitude square, okay? So these energy is always related to the amplitude square, okay? Okay. One more thing before I jump into the example, okay? It's that a lot of times, instead of trying to measure the power of a wave, we're actually more interested in the intensity of the wave. What does the intensity means, okay? So if there was a car, a car playing really loud music in the parking lot, it's not, well, even if I was outside, it's not going to be very loud as long as you're far away from it, right? But if you're right next to the car, it's going to be really loud, right? So being near a speaker makes things very loud. And that loudness is basically the intensity of that wave that's hitting you, well, hitting your ear and then causing noise in your head, right? So the way we can figure out how intense a wave is that you imagine you have a source of the wave, right? Just imagine the car in the parking lot playing some loud music, okay? As the sound wave propagates outward, okay, it's the same amount of power is being distributed amongst a bigger and bigger and bigger sphere. That makes sense? Okay, right? Just like, okay. So the intensity actually goes down as the surface area of the sphere that it covers, okay? So let's say this, particular wave is producing 10 watts of power, right? If it's distributed amongst, 1 square meters, right, that'll have some intensity. But then if it has to distribute it amongst 100 square meters instead, it'll be 100 times less intense because that sound energy is being distributed amongst a bigger and bigger area, okay? So in order to calculate the intensity, let me just give you the equation, okay? Right? The intensity for a wave that's radiating outward spherically, this is only the case if it's radiating spherically, is basically the power, whatever power you calculate it, using that complicated formula up top, so you want to write this one down, okay? Divided by basically the surface area of a sphere, 4 pi times the radius of that sphere square, okay? Okay. So this is the power we found before, right? And this is the surface area. The surface area of a sphere. Okay. Okay. That's what those 4 pi r squared means. Okay. Because the bigger that sphere, the less power per area it gives. Okay. The less intense that sound is. Okay. So it's not as loud. Okay. All right. Before I go on to the example and then the worksheet, which Ethan has, any questions? So I went through those that derivation stuff pretty quickly. It's also basically step by step in the textbook. Okay. So if you want to follow that, you can have that in the textbook. Okay, so let's do a quick example, and then we'll jump into our worksheet. Okay, we're gonna have a little wave on a string example. We have a 2 meter long string that has a mass of 70 grams. Okay, so as soon as I read this, I'm thinking, wait, why are they giving me the length and the mass of the string, right? That actually, it doesn't directly tell me something I need, but indirectly tells me the mass density, right? So the information I'm gathering from this, right, is that the length of the string is 2 meters. The mass of the string is 70 gram, okay? In other words, 70 times 10 to the negative 3 kilograms. Remember, SI units for mass is kilogram, not grams. Okay, so that tells me the mass density, right, is the mass divided by the length, right? That's actually 70. I'm gonna convert this to 70. That reduces by 1, right? Okay, just writing the same number, 2.00 meter. In other words, it's 3.5 times 10 to the negative 2 kilogram per meter, okay? So that's the information I'm gleaning from this, okay? Okay. And the string is under some tension. Remember, in this case, we want to write F sub T, the tension force is 90 Newton, okay? And it's oscillating at some frequency of 60 hertz, okay? Okay. And it has an amplitude of 4.00 centimeter. In other words, 4.00 times 10 to the negative 2 meters, right? Okay. And what they ask you for is the time average power supplied by the string vibrator. Okay. The time average is just all that integration we did. Okay. So don't worry about the time average. Okay. So we want to figure out what the power is. Okay. Power. Okay. That's the big question mark. Okay. So what we're going to do, right, to solve this, we have the equation for power is this 1/2 mu amplitude square omega square speed of the wave without a square. Okay, so a lot of variables in here. So let's make sure we have all of them, right? The mass density, we just calculated up here. Okay, the amplitude was given to us. Omega, where do we find omega? Anyone wants to give me a suggestion? Right. Omega is 2 pi times the frequency, right? We can actually calculate what that is if I have a calculator. So 2 pi 6.28 times 60. This is actually, I'm going to move this p over. It's just in the way. Okay. 376.8. And this will have units of radians per second. Okay. So that's another check. How about the speed of the wave? How do we figure out the speed of the wave? That's the more complicated one. So we use this variable already. We use this variable already. We use this variable already. What else is not used so far? Anyone have an idea? The tension, right? How's the tension related to the speed of the wave? The square root thing, right? It's the tension divided by the mass density. So we can actually calculate this. So the tension is 90 newtons, okay? And we divide that by the mass density, which is this number up here, -2. And then we square root the whole thing, okay, 90. divided by 5, 2, square root the whole thing. I got 50.71 meters per second. Okay, if you plug this number over here and that number over here. Okay, all right. So now we have everything we need. Let's do that red check too. So we can actually calculate the power. Okay, so the power is 1/2 mu, right? It's 3.5 times 10 to the negative 2, and that's an SI unit. Good. 4.00, that's the amplitude. Okay, and that's also an SI unit, but don't forget to square it. Okay, the angular frequency, right, is 376.8. That's also an SI unit, so we can just square it. And the speed, we wrote in SI unit also. Okay, so all of this should come out in SI units. Does anyone remember what the SI units for power is? Think about that. Why I punch stuff in the calculator? I'm sorry? Joules per, that's energy. Power is what? It's what? A watt. It's a joule per second, okay? Power is how much energy per second you're sending. Sorry, I lost track of my calculator. So I have to type everything again. 2 times E negative 2 squared times 376.8 squared times 50.71, okay? So the number I got was, how many sig figs we're dealing with? 3. I got 101 watts, okay? In other words, same thing as joules per second, okay? I'm going to add one more thing so we can do a little practice with intensity also. Okay. So I added the part B. So if this sound was emitted spherically, what is the intensity of the wave if we were 0.5 meter away, half a meter away? Okay. So intensity is just related to power divided by the area of the sphere that we're dealing with. Since we're dealing with a spherically outward wave, we just need the surface area of the sphere. Okay. Surface area of a sphere. Okay, so the power is 101, and then the bottom is 4 pi. The radius we're dealing with is 0.5 meters squared, right? So that's all in SI units. Divide by 4, divide by 3.14, divide by 0.5 squared. You punch out in your calculator, you get 32.1. Okay, this will have units of watts per meter square, right? Because this is meters, right, square, and this is units of watts. Okay. So unfortunately, the SI units for intensity is just watts per meter square. There's no special name for it, okay? Okay, Ethan, do you want to pass out the worksheet? While he's doing that, do you guys have any questions about this? Okay, a lot of it is just figuring out what all these variables are, okay? And then putting the intensity, yeah. The radius is given in my little flash when I talk about up here. If this wave was emitted spherically, what is the intensity when we're 0.5 meters away? Okay, that's basically how far you are away from the source. Okay, it's a good question. Sorry, I skipped over that.